All right, so let's look at some examples of applications of the sampling distribution of the sample mean. So I want to focus on, here we have a picture of a bell-shaped curve. This represents a sampling distribution for this random variable, our sample mean x bar. And we see here there's an indication that this distribution is centered at 12. So that's the mean. And then we have lines here at the inflection points. So I know that this is the mean, and this is the mean plus a standard deviation, and this is the mean minus a standard deviation. And this is a sampling distribution, so this is the mean for x bar, and both of these technically have little subscripts below them of x bar. All right, so that's going to make our first couple of questions pretty easy. Says, what is the value of the mean of the sampling distribution of x bar? The sampling distribution of the sample mean. Well, that's the value that we see here of 12. So that's in the center of this distribution. And then what's the value of remember that this is called the standard error of the mean, or the standard deviation in the sampling distribution of the sample mean. Well, that is this distance, basically. And so if this is at 12 and this is 12.05, then one standard deviation or one standard error of the mean must be 0.05. Now, the next part says, if the sample size is 9, what is likely true about the shape of the population? So that is a relatively small sample size. It's certainly less than 30. Now, we see that this sampling distribution has a nice bell shape. Now, what that likely means is that the population is normal, and that's why we're still getting this nice normal distribution even though the sample size is small. If the population were not normal, with this small of a sample, we probably would not get a nice bell-shaped distribution. All right. The next part says, what is the probability that a sample mean would be greater than 12.1? So 12.1 is somewhere over here. Let's see. And I went greater than, so I'm looking for the area that's under this curve to the right of that. Remember that this goes on and on forever. And so I'm going to go to my calculator and say I need a distribution, the normal CDF, and I want to look at from 12.1 up to infinity, so I'm going to use 10 to the 99th power for a distribution that's centered at 12 with a standard deviation of 0.05. And the area that's here under this curve is 0.0228, and I'm just going to keep 4 decimal places for this. All right. What about the probability that a sample mean is less than 11.93? Well, that's somewhere over here, and this is a less than statement, so I want to go to the left. And so again, I'm going to use my normal CDF function, and this time the leftmost point is negative infinity, so I'm going to use a really large negative number, negative 10 to the 99th power. And for the upper bound, that is 11.93. This distribution is centered at 12 with a standard deviation of 0.05. And so that probability is 0.0808. So about 8% chance of that happening. All right, and then what's the probability that a sample mean would be between 11.98 and 12.02? Once again, normal CDF. In this case, we're given a lower bound of 11.98, an upper bound of 12.02, and the center is 12, and the standard deviation is 0.05. So that is 0.3108. So there are some questions about this particular sampling distribution. All right, let's look at another question. this time we're told that a simple random sample of size n equals 20 is obtained from a normal population with a mean of 64 and a standard deviation of 17. This is we're concerned about the sampling distribution. So first, sketch a curve representing the sampling distribution of our sample mean. So is it going to be bell-shaped? Well, the population is normal, so my sampling distribution is also going to be normal. So I can draw a bell shape, and the center, it will have the same mean as the population, so 64, but the standard deviation in the sampling distribution will be a fraction of the population standard deviation. So I need to take this value sigma and divide it by the square root of n. That's the square root of 20. So if I take 17 and divide that by the square root of 20, it's about 3.8. So this is about 3.8. So 1, 2, 3, 1, 2, 3. This is 64. And if I add 3.8, this would be 67.8. And if I subtract 3.8, this would be 60.2. And of course, you could keep adding, like if I take 64 plus 3.8 plus 3.8, this would be 71.6 plus 3.8, and this would be 75.4. And going in the other direction, if I take 64 minus 3.8 minus 3.8, that's 56.4 minus 3.8 again, and this is 52.6. So those are the values where I could say, for instance, that 68% are between 60.2 and 67.8. 95% are between these values, and 99.7% are between here and here. All right, so that takes care of the first part. Determine the probability that a sample mean is less than 67.3. So 67.3 would be somewhere over here. So I'm looking for the area that's to the left of that. So I'll go back to my distribution menu, select the normal CDF. This starts at negative infinity, so negative 10 to the 99th power. And I'm going up to 67.3 for a distribution centered at 64 with a standard deviation. Now, you can just type in 17 divided by the square root of 20 if you want a really accurate calculation. That's the 80.7%. The probability that a sample mean is greater than or equal to 65.2. So 65.2, so I'm looking, basically somewhere around here is 65.2. And this time it's a greater than statement. So I'm looking for the area to the right of that. So I'm going to use my normal CDF function with 65.2 and 10 to the 99th power, 64, and in this case I'm just going to use my 3.8. I think that would be sufficiently accurate, and say that this is 37.6%. Now, compare the probability that x is less than 67.3 and the probability that x is greater than 65.2. Now, notice here, these do not say x bar. So, just to be clear, in this question, we're looking at the distribution, the population distribution, which is centered at 64, but with standard deviation of 17. So this would be 64 plus 17, plus 7 would be 71, that'd be 81, and let's see, 64 minus 17 is 47. Okay, so the probability that just a single observation is less than 67.3. So 67.3 now is somewhere over here. So I'll go to my distribution menu to normal CDF, and negative 10 to the 99th power, and my upper bound is going to be 67.3. This distribution is centered at 64, but with a standard deviation not of 3.8, but of 17. So that is 57.7%. Now that's compared to in the previous question where it was 80.7%. So this is quite a bit. This is in the population, and this is in the sampling distribution. Now the reason for this discrepancy is that the standard deviation is so much smaller in the sampling distribution than it is in the population distribution, where it's 17. And if we wanted to do the second part of this, the probability that a single observation is more than 65.2. So that would be wherever 65.2 is. I'm going to use my normal CDF, 65.2, 10 to the 99th for my upper bound, centered at 64 with standard deviation 17, and that is 47.2%. And so it goes from just about a 38% chance to a 47% chance. Again, that's just as my standard deviation there increases. All right, so what effect does increasing sample size have on the probabilities? So there's a hint here. It says try n equals 100. So if I change n equals 100, what's going to happen is that this denominator, instead of being the square root of 20, would be the square root of 100. And the square root of 100 is 10, and 17 divided by 10, this would drop down to 1.7. So I'm just going to do one of these. Let's recalculate this, the probability that x bar is less than 67.3. So I'll go back to my distribution function, the normal CDF. Now less than 67.3, so I'm going to need to start at negative infinity. Again, I'm tricking my calculator by using this very large negative number. And the upper bound is going to be 67.3. I'm centered at 64, but this time the standard deviation is 1.7. So that probability, when I change this to n equals 100, the probability that x bar is less than 67.3 is now 97.4%. I should have put a decimal there. It's 97.4%. So it went from 80% with a sample size of, let's see, what was that? With a sample size of 20. If I was just taking a single observation, that was only 57%. But with a sample of 20, the probability that the mean is less than 67.3 is about 81%. If I up the sample size to 100, the probability that the sample mean is less than 67.3 is getting close to 100%. All right, let's do one more example. The upper leg length for males who are between 20 and 29 is normally distributed with a mean length of 43.7 centimeters and a standard deviation of 4.2 centimeters. What is the probability that a randomly selected 20 to 29-year-old male has an upper leg length less than 40? Now, the key here is in the first question, it's just a single randomly selected male. So we're not taking a sample in this first question, so we want to consider the population distribution. So the population distribution is normal. It's centered at 43.7 with a standard deviation of 4.2. And so I'm looking for less than 40. So somewhere over here is 40, and I want the area that's to the left of 40. So for my lower bound, I'm going to use negative 10 to the 99th. For my upper bound, I'll use 40. For mu, I'll use 43.7, and for sigma, 4.2. So normal CDF, negative 10 to the 99th power, 40, 43.7, and 4.2. So that area or probability is 18.9%. All right. Now, in the next question, we say a random sample. Okay, so this is a sample of 9 is obtained. What is the probability that the mean? So we're looking for the probability that x bar is less than 40. That's a different question because now I need to consider the sampling distribution. So it's still centered at 43.7, but the standard error of the mean, so sigma of x bar, is 4.2 divided by the square root of 9. In other words, 4.2 divided by 3, which is 1.4. So I'm still looking at an area to the left, and this is 40. So I'm going from 10 to the negative 10 to the 99th up to 40, but this is the only value that's changing. So again, I'll use my normal distribution CDF function, negative 10 to the 99th power, 40 for the upper bound, 43.7 for the mean, and then 1.4 for the standard deviation. And now this is just 0.0041, so less than 1%. So in the population, there's about a 19% chance of that happening, whereas in the sampling distribution, there's a less than 1% chance. So is either unusual? I'd say yes. The second one there, where you're looking at that you would have x bar less than 40. That would be very unusual, less than 1% chance. Now, finally, there's a 10% chance that the sample mean, x bar, for a random sample of 9 males will be at or below. So in this case, I'm trying to figure out where the cutoff point is so that 10% is below this, which would mean 90% is above. So what is the sample mean? That it's the dividing line between that. So that's an inverse problem, and I'm using n equals 9, so I need to use my sampling standard deviation, which is 1.4. So I'll go back to my distribution menu, option 3. The area to the left is 0.1. The center is 43.7, and my standard deviation is 1.4. So the cutoff that will do it is 41.9, and that's in centimeters. All right, so there are some examples with applications of the sampling distribution for the sample mean.